Hi everyone, today we're continuing our conversation on buffers with topic 8.9, the Henderson-Hasselbalch equation. So, let's consider for weak acid, if I have HA plus water, that's in equilibrium with H3O plus and A minus. And we said a buffer is a mixture of HA and A minus in a solution, such that you have both at a similar concentration. Well, there's actually a really interesting math we can do to figure out the pH of a buffer. So let's think about our acid dissociation constant, Ka. That is concentration of H3O plus times concentration of A minus divided by concentration of HA. Well, we know that this can be used to calculate pH, and we know that from this we can calculate pKa, and the way we do that is we take the minus log. And so let's do that for both sides. Let's do minus log Ka, and let's take the minus log of the other side. We'll have minus log concentration of H3O plus, and we can just loop everything into its own minus log over here. Concentration of A minus divided by concentration of HA. And so now we have a relationship here where the pKa, right, because this is essentially just pKa, is related to pH. And so let's rearrange. Minus log concentration of H3O plus is equal to a minus log of Ka plus the log concentration of A minus over concentration of HA. Now, if we sub in, or at least take the minus logs of everything, what we'll see is we get this new equation. The pH, which is minus log of H3O plus, is equal to the pKa, which is minus log of Ka, plus the log concentration of conjugate base over the concentration of acid. This is the Henderson-Hasselbalch equation. In other words, I'm going to write this in all caps. For a buffer, you can use this equation. And so if I give you, for example, the pKa or the Ka of a weak acid, and I tell you the concentration of conjugate base as well as acid in solution, I can find the pH of that. Another situation where you can use this, and we discussed this in 8.4, but I didn't go into it too much, is a reaction between a weak acid and a strong base, where the weak acid is in excess. That's essentially the definition of a buffer, is that you have more weak acid than strong base, and you just haven't fully reached the equivalence point. When it's in excess, you can use the Henderson-Hasselbalch equation. When it isn't, then of course you have to use methods that we've previously talked about. So we can use the Henderson-Hasselbalch to find pH, but you can also use it to find the pK of an unknown acid. And so here, this example says the pH of human blood is about 7.4, right? Slightly basic. And our bodies use this carbonate buffer system that allows us to kind of have this equilibrium. The CO2 that we breathe out plus water can make carbonic acid. That can then react to make bicarbonate anion, which is HCO3 minus, and H3O plus. This is a carbonation of carbonic acid is approximately 0.0012 molar, and the concentration of hydrogen carbonate, or bicarbonate, is HCO3 minus, and that's about 0.024 molar. It's saying using the Henderson-Hasselbalch, find the pKa of carbonic acid at body temperature. This is a typo here. we're given pH and we're trying to find pKa. And so the Henderson-Hasselbalch equation says pH is equal to pKa plus log concentration of A minus over concentration of HA. We know pH, that's 7.4. We want pKa, and we're also given concentration of A minus, which is here. That's 0.024. And we know concentration of HA. And so all we do at this point is rearrange and solve for pKa. So pKa is equal to 7.4 minus log 0.024 divided by 0.0012. And we find pKa is equal to about 6.1. So using this method, you can find pH or pKa given concentrations. So let's look at this practice problem here. We have lactic acid and sodium lactate buffer. Lactic acid I'm just going to call La, and sodium lactate I'm going to call SL. The lactic acid is 40 milliliters and 0.5 molar. The sodium lactate is 200 milliliters and 1 molar. And so what we want here at the end is we want the pH. Of course, if we want the pH, we should use the Henderson-Hasselbalch. Plus log concentration of A minus over concentration of HA. And so all I got to do is find these two concentrations and then plug it in. We're, of course, given the concentration here, but remember, we dilute it by reacting them together. And so in any of these reactions, you need to consider the fact that you are diluting it. And so first, let's figure out what my new concentrations are for lactic acid. It's 0.50 molar times 0.040 liters. That's 0.02 moles. And then for sodium lactate, I can do the same thing. 1.0, 0.200. I'm just converting here from milliliters to liters. That gets us 0.20 moles. And then we just divide it by the new volume. The new volume is 200 milliliters plus 40 milliliters, which is 240 milliliters. And that's the same thing as 0.240 liters, because we just divide by 1,000. So I just divide both of these by the new volume. And I get, for this top one, for lactic acid, I get 0.083 molar. And for sodium lactate, I get 0.83 molar. And I'm not worried too much about sig figs here. We should have 2 at the end of the day. I'm just kind of going through this quickly so you see how the math works out. And so now I can just plug this in to my equation for the Henderson-Hasselbalch equation, or plug it into the Henderson-Hasselbalch equation. And so pH, that's what I'm trying to find, equals pKa, which I'm told is 3.08, plus log of 0.83 divided by 0.083. I can simplify this. It'll be 3.08 plus log of 10. Log of 10 is just equal to 1, and so pH is just 3.08 plus 1, which is 4.08. That is answer choice D. So the answer here is D. And so anytime you have a problem where you have a buffer or you have more weak acid than strong base, you can use the Henderson-Hasselbalch equation. So it's just another equation for you to keep in mind. It is on your reference sheet, but it will make these problems significantly easier. That's all for now. We'll continue this in class. Thanks, guys.